All the time. That makes you a badass.
It's like a big ass, it says Moscow. Never rides it.
Yeah, we should go out like this sometimes. It's really nice to get like Balboa Park.
All of that going. I'm not fast, but is that the start time and the end point? I'll eventually.
All right, guys.
But I like riding.
So we're going to derive one identity directly. There's three what they call fundamental identities in Trig. All you really need to know is one, because the other two are based off of that one. And again, my continual theme is I hate memorization. Let me figure out ways to stay away from that. So if you want to memorize all of them, feel free. What's Trig, or what's x squared plus y squared?
H squared.
H squared, 11. So if I take sine squared of something of an angle plus cosine squared of an angle.
Tangent squared? Hypotenuse squared?
I like it. We don't know yet. What is sine defined to be for a given triangle?
X over H.
Yeah, so sine is y over h. Cosine is
H over
X over H.
X over H.
x over h. Now do this work. What do you get? You get y squared plus x squared over h squared. Is that cool? And what's y squared plus x squared?
H squared.
H squared. Which is 1. It should only really make sense. Sine goes like y, cosine goes like x. We just said x squared plus y squared is 1, so it should make sense that this comes out to be 1. Yeah?
How do you go from y squared plus x squared to x squared on the top?
Given this triangle. Yeah, cool.
Thank you.
You're welcome. I like that. My explanation is point. Very effective teaching. So that is the most fundamental trig identity there is. A slightly different way to look at this is, I don't know if you remember, but the definition of a point on the unit circle is basically that this has to be true. So the point sine theta comma cosine theta is on the unit circle. Does that make sense? In fact, that's basically the handout I gave you. Every single one of these where it's got this is cosine theta comma sine theta. Let me say that the right way around. X comma y. So of course this is true. That's the definition of anything sitting on the unit circle. That has to be true. This is a little bit more rigorous of a proof. But there you go. That's exciting. Now if you take this fundamental identity, divide both sides by cosine squared. Just because. What do you get? What's sine over cosine? Tangent. So you get tangent squared. Cool. Tangent squared plus 1. I love it. Equals. Beautiful. 1 over cosine is secant. C goes to S. S goes to C. All right, there's identity number 2. You see how you do not have to memorize the damn thing. And another really cool thing is there are no cos in that statement, are there? No cos. You with me? No cosecant, no cotangent. The other one, if I take sine squared and this time I divide by this thing by sine squared, what do I get now? I get 1 plus cotangent squared equals cosecant squared. Now you got the one that has all the cos in it, right? That's another little aid to memorization if you want it. So how the hell is this useful? Well, if I said given cosine theta equals 3/8, and theta is in quadrant 4. Find sine theta. I know right that way I can't do it. Find sine theta. You could actually use this formula if you wanted to, right? Just plug in what we know. I don't know what sine is, but I know cosine is 3/8. And you see why you need the quadrant 4 information? Maybe. Because at some point I got to take a square root, there's going to be a plus or minus, and that's going to tell me which one it's going to be. So sine squared, 1 minus, I don't totally trust my math ability today. Sine squared equals 55. So then sine theta, is it going to be plus or minus? It's going to have to be negative because I'm in quadrant 4. Y is negative in quadrant 4. Cool. You guys kind of with me? Now, that is the most basic place that this basic identity will show up. This thing becomes incredibly useful. You love it when you see this because you can replace it with 1. That kicks ass. So it shows up in a lot of different places. Trying to simplify larger trig problems. You see sine squared plus cosine squared somewhere. 1. Sweet. Very nice. Okay, so we have 3 identities up here on the board. You must know them. I'm suggesting you really only need to memorize this one because you can build those one off of this. You good? All right. Now, just to let you know, there are going to be, I've got a sheet like this filled with identities. I'm going to make it very clear for the next test which identities you must memorize. I'm not going to make you memorize all of them. I'm going to make you memorize the ones that I have somehow memorized. Right? I'm not going to make you memorize. There are several of them I don't want to memorize. I'm not going to make you memorize them either. So I'll give you those. The other ones you will have to know yourself. Right now you got to know these.
You read, and then practice with it. I think that's really
Oh! All right. So, yeah. I'll tell you what. Before I do 5-3, oh, that's hold off on that. Do 6-2 real quick. 6-2 is the section that really gets into what's the immediate use of trig functions in the real world. Kind of a nice section to have, right? And you have a lot of classic problems in this section that are kind of lame. The one about the ladder laying up against the side of a building. And you know how far away from the building the ladder is, some crap like that. Some of you guys are shaking your head like you know what I'm talking about. But you know, one of the more interesting ones are, if you know, for example, here's a tree. This is my awesome drawing capability. Oh, this poor tree's seen better days. Okay. All right, here's Jeff. Yeah. See, this is why they would never let me teach art.
I don't think you tried very hard.
Huh? No, this is actually this is my best. If I want to know how tall this tree is, and I happen to have a certain little instrument that I could use to tell me what the angle is. So let's say I know that the angle from the ground to the top of the tree. Let's say this is. Let's go for the real
Leaves, not blue.
Yeah, I guess we'll include the leaves. Why not? It'll be nice. Should I like growing your hair really tall so you're tall? I almost sound like a personal experience. And You know that you're, let's say, you know that you're 20 feet from the tree, and you happen to know you got a little something that you can measure the angle with. It could even be something as simple as a protractor, but they have much better things to use. You know that the angle up to the tree is 28 degrees. That's it. It's like, okay, this is a decent sized tree, obviously not drawn to scale, obviously not drawn well either. But here's the idea, and at the same time I'm doing this problem, I'm going to introduce how to use your calculator to do this. Because do you know any trig functions of 28 degrees? No, and I'm not going to make you memorize every degree, sine, cosine, whatever, just the 30, 60, 90, and 45. So what, I'm curious about the height of this tree. So what ratios can I set up? What trig function would represent a ratio of something I want to know to something I know? So what's the only side that I know? The 20 degrees. So I need something using the x piece. And the side that I want to know is the y piece. So of course, what's the good trig function to use there? Tangents. Careful. Cosine would involve this side that I don't know a damn thing about. And I don't even know enough to be able to use Pythagorean theorem. So the tangent of 28 degrees. How did I know to use it? Because it's the one that makes sense. It relates what I want to know with what I know. I could have used cotangent too. Why not? Let's use tangent. Equals, yeah, in general it's y over x. 20. X is 20. Now, that is a beautiful illustration of an immediate real-life application of these ratios of sides of triangles. I mean, this. And if you really think about what this thing is saying, it's kind of dumb in a way. It's kind of like, well, duh. Tangent is this ratio. So, tangent of 28 degrees, my calculator can eat that up and just give me a freaking number. We used to have tables of tangent and sine and cosine, and thank God we have calculators now that have all those tables to memorize. Or in their data banks. How do I solve this for y?
Negative 0.28.
20 times tangent of 28. Now, here's the next piece of this. Of course, I always forget. I want to put something on the overhead, not to use that middle board. That's too bad. Here's my word of warning. And this is how easy it is to do this. I once took an entire test in the wrong mode. Because every problem happened to have the answer kind of made sense. If I do very often you'll do the wrong, I heard somebody say a negative number, which of course would be weird. The tree grew down or something. I don't know what that means, right? But that might mean you have your calculator set to radians when we actually have degrees in the problem. You with me? So I got a 0 on the damn thing. I set everything up right. I just have to have the stupid calculator in the wrong mode. Nothing came out negative. You know what I'm saying? There's no immediate proof that I was doing something wrong. So you must be careful about what mode your calculator in.
You seriously got a 0?
Yeah, apparently they didn't.
I don't think you would give us a 0 back
No. That's the guy that the highest grade was a B
What it means
in his
to
class,
have gone
which
through
was me.
like all these questions.
I was pissed.
Even if they were wrong,
And it was a B.
Like overall?
He said if God was in his class, he would still get like an A minus. I made the rule, screw it. A minus, dude.
So we need to switch the mode every time?
Well, the really nice thing about this, the way that they set up these sections, chapter 5 is all radians, chapter 6 is all degrees. Now, the one thing I won't be nice about on the test is they'll be mixed up on the actual test. So you will have to be careful about changing your modes. Yes? Depending on what you got. Now, you could, if you always want to keep your mode radians, then you just always convert. If I give you degrees, convert it to radians. I really would rather not do that.
Yeah.
So step 1 here is, how the hell do I tell what mode my calculator is in?
Push mode.
You probably push the mode button. I like it.
Yep.
Maybe not be good at math, but I'm good at obvious.
So if you hit the mode button, you can see where this is. So right now I'm in radians. So I want to go over to degrees and hit enter. So now I'm in degree mode.
Do what's gradient?
When are you gonna grid the
There's,
I'll let Captain Obvious take it.
there's another mode on here.
If I reach Captain Steps,
What's up? Oh, there's other stuff on here. We'll actually run into some of these. We'll run into these two later this semester. Parametric and polar. Yay. What else? Oh, here's your complex number mode
that on the last
that I didn't tell you about.
test? Surprise, found it.
Some of you guys used it and made it a little too obvious that you used it. So.
some of us didn't need to use it, did we?
Not at all.
Dude. Or you hit it well enough. Okay. So everybody's in the right mode now. Your degrees. So now we can put in there 20 times, what was it? Not sine, tangent. 28. So if I was in the wrong mode, if I was in radians, yes. This won't happen often enough before, like, to me, if I would have gotten that, I would have went, oh shit, I'm in the wrong mode. But that didn't happen. So that should tell you automatically, please, dear God, don't write that down, right? Negative 5 foot tall. So the tree is how tall?
10.6.
Yeah, 10.6 feet.
Am I in the wrong mode? Why is this not working? I should put it in
You guys with me?
Find the calculator.
Yeah, let's double check a few things.
It's not good.
Don't write this in the calculator. What is sine of 45 degrees? All right, so if we take square root of 2 divided by 2, I get 0.707, blah, blah, blah. So if you do sine 45, oh yeah, I forgot. There's a good example, Jeff. Forgot I changed it earlier to mess myself up, and I messed myself up. There you go, same number there. 0.707, blah, blah, blah. So obviously, I think I said this earlier, but on this next test, I'm going to have a part 1 to the test. No calculators allowed. You turn that in, you get part 2. The calculators are allowed. Yeah. Aww. Takes you back to your math 88 days. All right. While I have the calculator up here, any questions about how to do anything in the calculator? Like, for example, how would you do cosecant of negative 1,048 degrees?
1 divided by the sine.
I love it. Cosecant is, now be careful, if you do shift sine, you get inverse sine, which we have not even talked about yet. So what's the input for a trig function always? What's the input for a trig function? I have an example right here. What's my input? That is it's a degree, which is a way to measure an angle. So the input for a trig function is always an angle measure. You with me? So what's the output of the inverse trig functions? An angle measure. Right? Don't they switch? The input of one is the output of the other one. So if I do inverse sine, I'm not going to get what I want. I'm going to get the angle that corresponds to a sine of this, which doesn't exist. You're going to get crap, basically. I want the true reciprocal of sine, not sine -1. That means inverse sine. That means the opposite function. That does not mean the reciprocal function.
I don't understand what
You
you're
were
saying.
right about
Understood.
sine for -1.
This
It's true.
is not that. That's the summary of everything I just said for the last few minutes. And we know this. We made a big point in this back when we first learned inverse functions. F inverse is not equal to 1 over f. We know that. Well, okay, sine is a function. In fact, we're going to look at its graph. We're going to see that it passes the Ripple line test. It's a function, so that's true for any function is f inverse is not equal to 1 over f. So specifically, sine inverse is not equal to 1 over sine. So if I want to do cosecant, I have to do 1 divided by sine of negative. I also have to use the right negative button. Okay. Hopefully I'm in the right, mode.
Yeah.
Yay. You guys,
Same thing with the cotangents as well.
exactly. Do 1 over tangent for cotangent, do 1 over cosine for secant. Cool. And just to show you, we haven't talked about it yet, But if I did inverse sine of 1/2, what should I get? Don't do it. So what's that asking? That's asking what angle has a sine of 1/2. So what angle has a sine of 1/2?
30.
Sine is biggest when it's close to y, so it's smaller when it's further from y. So it's got to be the 30. So if you do this, 30 degrees. So if you said 30, you were fine, but I heard 30 and 60. I couldn't say yes or no. Okay.
Yeah.
So it's like, I gotta go see everything. He's like, plus it happened in the
Say random thing.
So I feel like we spend like,
Especially good when it's a yes or no question. All right. So let's try one more problem like that.
She was like, so you have to be parents' taxes. Like, when you start, she was like, next year, he's gonna be like, sit down for years and like that. She's like, everywhere he drives now, all his meals,
That's another reason why I'm doing this.
yeah, he talks
All,
about
every drop of gasoline.
yeah, and like if you go like 5 down to whatever, you know, like one to one, you just slap your name on it. The company, you know, it's ridiculous. Yeah, she was like, he needs to talk to a professional, make sure he's doing it.
I need to. I do. I'm really going to get started here pretty soon because I don't have work right now.
Yeah. Hey, that reminds me, I go to state like constantly. So I was thinking, you give me some business cards when I go to the state.
I should try to do those 3 problems real quick.
I'm going to try and hand them out by hand so I don't want to make sure none of them get thrown away.
Yeah. I'm just letting you know. That's always
I'll bring something for you though.
because I was trying to figure like how can I repay this guy and pay him like that because well I can use some free marketing.
I had fun working on your bike though.
Yeah.
I
Fun
decided
like that. Yeah.
Hey, that's a tricky one there.
Trying to be confusing.
Okay, so top. Tangent is x over y. It's x over y.
Y over X.
Y over x.
Oh, yeah. They have problems just letting us know, so I want you guys to be ready for that.
I don't think you can. You just have to know tangent 49 degrees.
Because I'm waiting for the first event.
There it is. Found it.
All right, guys. Which trig function would you use in number 1?
Sine.
Because that relates the y piece to the hypotenuse, so sine of 40. I know.
X over
I like it.
12.
So x over 12. And then whatever that comes out to be.
7.71. And then a bunch of numbers.
You get 7.71. Blah, blah, blah. Is that what you guys get? Going by, just throwing it to the cloud. Just trust
That's
it.
what I got.
Now here, of course, what do you want to use here? Which trig? Cosine, because you got the x piece and the hypotenuse. So cosine of the angle and the base. It's always the angle and the base to make that kind of work. It is going to be whatever what?
6 over x.
6 over x. So then x equals 6 over cosine 15. And then whatever the hell that is.
6.21.
6.21?
Yes, sir.
Okay, cool. And why does that kind of make sense? Because it's obviously really not drawn to scale very well, but this side should be the longest side. 15 degrees opens up a lot less. This should be the shortest side. So I don't know how familiar you are with the Pythagorean theorem. If you have a side that's really long and the other side's not that long, the hypotenuse is going to be basically just a little bit over the longest side. If you've ever noticed that. If not, it will be. So what about this last guy here? The only thing you really have to do first is just, what's that angle going to be?
That flips. So it's going to be
60.
So tangent is going to be
41 degrees, right? To make it 180 degrees total.
180 minus 90 minus.
Or, yeah, you could do the right thing. You can either think of this as, you can either do SOHCAHTOA, or you could just think that's the y side, that's the x side, that's to put that in the base, or you could change the angle. Now, the interesting thing that brings up is something that we've said earlier, but we haven't really formalized yet. Sine of like 20 degrees, how does that relate to cosine of 70 degrees? Careful. That's true. 20, 70 is 90. So how do those two values relate? Sine of 20, so this piece, compared to cosine of 70, this piece. They're going to come out to be the same. They're going to come out to be equal. We saw that with 30 and 60. Don't the sine and cosine switch? Because it's going to grow, sine's going to grow until it's the same as cosine at 45 degrees, and then it's going to cosine's going to shrink. So they're growing and shrinking at the same kind of rate. So at 20 degrees, sine should be the same as cosine would be at 70. Right? So that's why you could either use that angle or that angle. It's going to come out the same way. One way you're going to use tangent, and the other way you're going to use cotangent. Right? Okay, maybe. So if you do it this way, yeah, you could do tangent and make it this over this. You could do that. Or I could say, if I wanted to, I could say cotangent of 41 degrees equals x over 11. Or you could say tangent of 41 degrees equals 11 over x. All those end up with the same answer. Maybe. I see a lot of people. Oh. Uh-oh. A lot of people agreeing with me. I'm going to really get it. So there's 3 different ways to do this problem. They're all basically the same way. Especially these two. It's just the reciprocal. Reciprocate that, boom. It's not amazing. This is the one that's a little bit more freaky. But it's really related to that idea there. Tangent of 49 is the same thing as cotangent of 41.
I feel like that one was easier because you had 7.
I like it. Whatever way makes the most sense. So if you do it this way, 11 tangent of 49 is x. And what do you get when you do that?
12.65.
12.65, blah, blah, blah. And why does it make sense it's a little bit bigger than that? Why does it make sense that that's a little bigger than that?
Because of the way the angles work out.
Because that angle opens wider than that one does. If it opens wider, the side has more room to sit, right? So that one gives this one more room to be longer. Cool. Okay. All right.
I don't know what it is, but this is a conversation. I feel like it's,
And one last little idea before we get into graphing. Oh my God.
A long time.
Oh my God. All right.
I was in my engineering class, it's a basic engineering class, and we're going
Wait.
to like 3 stations. And that key event, and we'll let you know that in my engineering class, and the teacher, about 10 to 15. That's how they use it to get out of 3 stations.
All right, guys, so the idea of, guys, the idea of arc length. How long is this arc that I'm traveling? So I know all the way around the circle is 2 pi r, for example, right? And actually, let's make this even simpler. Let's make this based on the, no, let's not do that. Let's not make it easy. Let's make it all the way out. Circumference is 2 pi r. So if I'm not quite at 360, if I'm at some angle less than 360 or less than 2 pi, I need to talk about the radians now, right? Because I'm talking about the distance around a circle. How do I figure out how long that is? This s would be 2 pi r if I went all the way around the circle. If I went halfway around the circle, it would of course be what? Let's say pi. Then s would be 1/2 of 2 pi r, right? You with me? And of course, that's pretty simple. If I went 1/4 of the way, if theta was pi over 2, then s would be what? What would I put there? That was when I went halfway around the circle, so now I'm going 1/4 of the way around the circle. So it'll be pi over 2r. Can anyone see a pattern developing here? Really, when I went pi, it was pi r. When I went pi over 2, it was pi over 2r. So the way to get there to really see it is if s is theta, I mean not s, if my angle is theta. How do you say that? The angle is theta. Sweet. Then all I have to do really is do theta out of 2 pi. That's the percentage I've gone around. 1/2, 1/4, or in general, theta over 2 pi. That's how far the percentages I've gone around the circle. Times what it would be if I went the whole way. And of course, what do you get there? R theta. So that's the arc length formula. And that's really the pattern you see if you do a few of them. It's just r times theta, r times theta. Theta here has got to be in radians. Degrees would not make a damn bit of sense here. Because they're just arbitrary. We just made them up.
What did you just say? Sorry.
When you use this formula, remember what I said earlier? If the angle is not inside a trig function, it must be in radians. The trig function takes the angle, whatever it looks like, and makes it into a value. It doesn't care what it looks like. They all reference the same angle. You with me? But if it's sitting outside of a trig function, then it's got to be a real number. And radians are the real numbers, not degrees. This has got to have the angle in radians. Now, the funky thing to me is, the next step of this is to figure out what the angle of this triangle would be. We could actually call it the area of the sector. What did it say, the angle of the triangle? The area of the triangle. It's not really a triangle, though, but I say that for a reason. Why is that not really a triangle? Because the curve's on the base. The base is curved. But the really funky thing is, let me show you the book way, and then I'll show you my way to explain why this is what it is. So I have this sector here, and I want to know the area. I can do it the same way we just did. The area of the whole circle would be pi r squared. So I can do it again. The area of that little sector, I'm going to call it AS, or like area sector. Let's just call it area. This area here, we'll call this one the area of the whole circle. This would be what we just did now, theta over 2 pi. Same idea. I'm still going to multiply by that percentage of the circle. That what percentage did I just cut out of the pi? Same kind of thing we used here. That represented the fractional part of the circle that we've gone around. Here, this is the fractional part of the circle that I'm covering to get the area. And what do you get when you do this? You get 1/2 theta. Let's just put it away. R squared theta. Now, that's nice. Nothing really wrong with that. But the really cool thing is, if I look at this thing like a triangle, and I know I can't, but I can now. What's the base? We just figured out this, didn't we? Isn't that r theta?
Yes.
All right, so the base is r theta. What's the height?
R.
R. Isn't the area of a triangle 1/2 the base times the height?
Yes, it is, Jeff.
Which is the same damn thing we just got over here. Now, to tell you honestly, you got to be careful when you do things like this. They don't always work out. The fact of the matter is, if this was straight across, the actual radius would be smaller. So the radius being longer actually fills in the missing part, the curved part. So those kind of work together really well. But I just love the way this works. And if any of you go to Calc 3, does anybody here maybe going to Calc 3? Try to remember this when you're doing different coordinate systems, three-dimensional different coordinate systems, calculus in like spherical coordinates. This becomes really useful.
I'm taking a photo.
I like it. So the mental photo.
It's stuck in my head. For
Mine degrade very quickly when I try to do
As long as I
that.
don't fail here in the next 2 years, I'll come right back.
So there's two little formulas there. So they ask you to find the area of a sector. That's, again, the angle's got to be in radians. So the area of a sector, let's say the radius is 12 feet, and my angle is, let me throw you off a little bit, 40 degrees. So I basically just told you something is you got to be careful about. Feet's not a problem. That's in degrees. It has to be in radians. So the first thing you want to do is change that into radians. How do you change 40 degrees into radians? Sounds like a really bad joke. That's right. 40 degrees times pi divided by 180 degrees. So the degrees cancel. So you get 2/9 pi. So area would be 1/2. Radius is 12 feet. Squared times 2 pi over 9. It's 16 pi, I think it is. 51 point something. Do I really trust my brain at the moment? I don't know. Is it 51 point something? I was close. 50.26 square feet. I like it. Give me out. Yeah. 27? I don't know. I'm going around it. 27. Okay. All right, cool. How's that? That's not too bad. You have two little formulas that you must know. Okay. And the really nice thing about that is it's not something you can do to prove anything, but it's certainly a way you can remember it easily. Hopefully. R theta base, R height, area is the same triangle formula we use forever. Yeah.
Is calculus like all circling type of crap? Or
No. The method you learn in calculus based on the rectangular coordinate system, you have to extend it to other possible coordinate systems. That's where this kind of thinking comes in really handy. It's very, my professors didn't like it when I did this kind of thing, but it always freaking worked, and I always made sure that it was balancing out with what was, So there's a lot of three-dimensional analysis you can do that makes it a lot easier if you look at it like a cube that's curved, but you just look at it like a normal cube, and you define each of the sides, and it makes it a lot easier. You'll see maybe when you get there you remember what I'm talking about. Got it. Video comes back. All right. So that was the last little bit. That was actually from section 6.1. Those two formulas. Yeah, arc length and area of a sector. I did the first couple out of 5 and 6, I think. I can't remember. Okay. So now we're going to do just a little bit out of 5.3, I think. And then we'll call it a day. Yeah, for the first day of that from break. That'll be plenty.
Which section were those from? Sorry, the arc length and the area?
This is from
6.3?
6.1.
Really, that's 6.1, right?
This is a pretty good big screen movie. It's going sucked, and then the killing starts. At the beginning, you're like, how cheesy could this possibly be? And then, like, the first killing goes down, like, oh my god, this is ridiculous.
All right, so we'll attack this the same way we always do. Whenever we hit a function we just learned and we want to graph it, we just make a table of values. Sounds almost too reasonable. So let's say, for example, I want to graph sine. Let's throw a negative value in there just to start it off. Why not? Well, we'll definitely do 0.
Maybe -1.
I'm going to do this in radians too, just to make it even better.
Yay!
Let's see. The nice thing is, a lot of trig stuff you just have to focus on the first quadrant, because then you can realize it's just going to change signs and kind of follow the pattern from there. I just want to throw in a negative one just because. So let's start with 0. What's sine of 0?
0.
Beautiful. There's no y piece when you're at 0 degrees. It's all x. Right? Do you see how nice it is to remember it like that instead of just memorizing sine 0, 0? What's sine of pi over 6? Pi over 6, of course, is also what degrees?
30.
30. So sine of 30.
1/2.
Now it starts to grow. So now it's kind of nice to follow the pattern. At pi over 4,
Square root of 2.
yeah, root 2 over 2. That's where they're the same. Then it grows a little more at pi over 3.
Square root of 3 over 2.
And then finally it reaches its extreme and the other extreme there. Yeah. And then it's going to go down from there again, right? What's negative pi over 6 going to be? Negative 1/2. I like it. Because negative pi over 6, y is going to be negative there. You guys semi with me? All right. Got way too used to Greg. Now, what kind of scale do we want to use here, considering the outputs of sine?
1, 1.
One.
Yeah, one big step of 1. Now you know that we can't just leave it at this. You know that we're going to talk about transformations of trig functions.
Yeah.
Moving them up and down, moving them left and right, squishing them, stretching them, all that kind of stuff. So here's my negative pi over 6. I got pi over 6, pi over 4. Let's do this a little bit more careful. I'm going to do a little less precise out here. Oops, not that less precise. My scale sucks, but we'll get over that. So negative pi over 6, it's at negative 1/2. Then it's at 0. Pi over 6 is at 1/2. Pi over 4, it's at root 2 over 2, which is about 0.7. Pi over 3, it's root 3 over 2, which is about, I don't know, 0.8 something. And pi over 2, it's at 1. Where is it at pi? And then it's going to come back down from there. Of course, this is really horrible scale, this thing. It's going to come back down from there, right? Goes up to the maximum. At pi, what's sine of pi?
1, 0.
Yeah, sine of pi is 0. It's back to the x-axis again, no y piece. So sine is going to be 0. 3 pi over 2, it's... make my scale better. So at pi, it's 0. At 3 pi over 2, it's down here. So it's not 1, it's negative 1. And then at 2 pi, it's back to 0. It goes on forever from there, and it goes on forever from there. That's a horrible graph, so I apologize. Try to be really precise here, and then not so much out there. My scale went freaky. But basically, this is what you expect. You already kind of know this shape. You've seen it in horror movies. If you're at all into music and you see the oscilloscopes, you see it all the time on the oscilloscopes. You know, this is the good old sine wave, right? So it starts at 0, it grows to its maximum, comes back down. That's exactly what we saw when we did the unit circle. What else? What can you tell me about the symmetry of this? Not my graph, but the sine graph in general. What kind of symmetry would it have? Even or odd? Even would be like x squared. Does it have that kind of symmetry? Hell no, that's not there. Odd symmetry through the origin, yeah. So sine of negative theta is negative sine theta. That's odd symmetry. So I bet you anything cosine will probably be even. Let's try to do cosine without making a table. So I got these are my anchor points. These are the anchor points you want to use when you're shifting it. These are the points you want to consider moving around. Pi over 2, pi, 3 pi over 2, 2 pi. That's your anchor points. We can go ahead and put a negative pi over 2 back there. Let it go, Jeff. You got your 1, you got your negative 1. Cosine is 0. Cosine likes x at 0 degrees is all x, so cosine of 0 is 1. Cosine likes x, so when it's on the x-axis, it's one of its extremes. All 1 or all negative 1. Pi over 2. 0. Because now it's all y. No x for cosine alike, so there's nothing there. 0. At pi, negative 1, because now it's back there. Well, for you guys, yeah, back there. Negative 1 on the x-axis. And then back to 0. And then back to 1. At negative pi over 2, it'll be 0. This is one cycle. Here's one cycle. Actually, a cycle in general is you start somewhere and you come back to that same point going in the same direction. How long does it take to go through all of its values? That's a cycle. That's going to become important when we start shifting this, because how far does this go forever in both directions? So when you shift it, you want to focus on a central cycle and then shift that cycle around. Put little arrows on the end to cover yourself. Goes forever that way. What's kind of freaky here, because I keep talking about eventually we're going to learn inverse trig functions. What's kind of wrong with what you see related to looking at the inverse of these things? What does it not do it's supposed to do? It doesn't pass some kind of test. Horizontal. It passes the vertical line test. It's a function. It does not pass the horizontal line test. Which means, what do we have to do before we can get inverse functions? Restrict the domain. I love it. So I can do a parabola as long as I cut half of it off, and then all of a sudden it's invertible. It passes the horizontal line test. So here we're going to have to figure out where do we want to restrict our domain to get our inverse trig. Thankfully, it's still in our future. Now, so those two, notice something about these two. Trying to get over this one's mutation. How are they kind of related to each other? The shape is totally the same, but if I took this and moved it, how much would it suddenly become this? Half what? Not half, but pi over 2. If I moved it over by pi over 2, they would be the same. So they're out of phase by 90 degrees. That sounds kind of cool. Sine and cosine are out of phase by 90 degrees from each other. I'd have to move cosine by 90 degrees to the right. How could I accomplish that? How can I represent that? Cosine of what would make it move? X minus. Right? Now, here's the thing. Cosine, what kind of function is it? Even or odd?
Even.
Why is it even? Because it's like a x squared. It's symmetric along the around the y-axis. So that's an even function, which means cosine of negative x is the same thing as cosine of x. Cosine of negative, let's see, this is the same thing as cosine is positive that, with the same output. That's what even means. So this is the same thing as that. And that's what you always see. You always see cosine of pi over 2 minus x equals sine of x. Still means they're just offset by 90 degrees. But when you look on page, let me see where they have this. I have no idea where they have it. Somewhere in there. But they always have this as being cosine of this equals sine. That represents that they're offset by 90 degrees. The last one, before we're not even going to do the inverse, not the but the reciprocal trig functions today. We'll do that later. What about tangent? The hell is that thing going to look like? Where's tangent going to have problems? Considering that tangent is sine over cosine? Where's it going to have problems? Yeah, it's going to have vertical asymptotes. Where? Where will it have vertical asymptotes?
At each of the 0.
Cosine theta is 0. Where is cosine theta 0? It's 0 at an infinite number of places. Give me one.
Pi
Careful.
over 2.
I like it. So this is theta equals pi over 2. But it's also any plus pi, 3 pi over 2, plus another pi, 5 pi over 2. It's at any pi over 2 plus pi, or any, let's say it like this, pi over 2 plus pi k. Just think about that for a second. It's 0 at pi over 2. It's 0 again if you add pi to that. 0 down here again. 0 if you add another pi to it. It's 0 if you subtract several pi's from it. Anytime I end up on the y-axis, cosine is going to be 0. So it's 0 at pi over 2 plus pi k, where k is any integer. Does that make sense? It's definitely 0 at pi over 2. And if I add pi to it, it's 0 again. If I subtract and multiple pi from it, it's 0 again. That's exactly what that little statement means. So that means tangent is going to have a vertical asymptote at those positions, which means it's going to have to slam up against that somehow. And if I try to make this table real quick, tangent of 0 is,
Tangent of 0.
what sine is 0?
What?
1.
Oh,
0
0.
over 1.
Must be 0.
0.
Can't be that one, must be the other one. Tangent of 0 is 0. Tangent of, what's tangent of pi over 4? That's the nice one.
1.
That's
Yeah, that's where sine and cosine are the same, so tangent's 1. Tangent of pi over 6 and pi over 3. Pi over 6 is where cosine is bigger. So it's going to be 1 over root 3 or root 3 over 3. Pi over 3 is where sine is bigger. Right? 60 degrees sine is bigger because it's closer to the y-axis. That's going to be the one that's just root 3 over 1. Woo! So here's what it looks like. 0 at 0. At all the pi over 2's, it's got vertical asymptotes. 1 pi over 2, 3 pi over 2, not 2 pi over 2, that's fine. So it's like all the odd multiples of pi over 2. Does that make sense? No, but just keep going. All right. At pi over 4, it's 1. At pi over, negative pi over 4, what do you think it's going to be? Negative 1, sweet. So effectively, it ends up looking like this. It ends up looking almost what?
like a x cubed.
Cubish, yeah, cool. And it not only looks like that, it looks like that forever. Continuing. Same way as sine and cosine just have are nice because their cycles happen to meet each other forever and ever and ever. Tangent, no, the ends go to infinity, so how could it meet? Oh well, so now it looks a little freakier than we want it to. Let's do that. But it still has to go forever. Because I can do the tangent of 50 billion degrees. It's way the hell up there, but it looks the same. Okay, you guys? Cool. So if you look at the handout I gave you, hear what we just talked about with those top 3. The bottom 3 are the reciprocal functions. So on this one it gets a little more technical. The domain, the range, and the period is really how long does it take one cycle to go through? How long does it take for one cycle to show up? It takes, for sine and cosine both, it takes 2 pi. But what about for tangent?
Pi.
Yeah, from negative pi over 2 to pi over 2, that's one cycle. So its period is pi. So period really just means how long does it fit? Does one cycle fit in? Okay, cool. So when we start stretching these things or compressing these things, we've got to figure out how does the period change.
So in tangents, we cannot do the transformations.
Yeah.
Once we have the tangent, we can do the transformation.
Definitely we can. And we will. Yeah. I think that's plenty. My voice is starting to go.